Hey guys, so in today's video we're going to be looking at motion graphs, distance versus time, velocity versus time, and the types of information that we can get from those graphs. So we're going to go ahead and start with a student's work from the ball dropping lab that we did a couple of classes ago and see what we can get from that. Alright?
So here's the student graph that we're going to look at to try to make some sense of what graphs are trying to tell us. We talked a little bit about this in class, but I want to make sure that we're really putting these ideas together with some of the things that you've learned in your math classes. Now, I did choose this student work for a specific reason. Number one, they've got some good data here, right? And good data is always important to make sure that we're seeing what we hope to see. Number two, the student included the origin, right? That was not one of the data points in the table, but they realized that for this situation, if there was 0 time, the ball should have traveled 0 distance. And so they included 0, 0 there, which that's the only point that I'm actually 100% sure of. All the other points, there could be any amount of error or, anything going on there, friction that we ignored, anything can go on. So I like that he used that point. Number three, used a ruler for all straight lines. Even if it's just the sides, the axes there, if it is a straight line, you should use a ruler for it. And this student did that. Number four, they used most of the paper here to cover the graph. I do think that possibly they could have used a little bit more space, stretch that graph out a little bit with the bottom, and I'll talk about that in a second. But for the most part, they did a good job of not squeezing the graph into a very small area. It's nice and spread out. Last of all, they did not do the kindergarten connect the dots, just draw a line to each dot, because that doesn't mean anything to us. What means, or what will mean something to us, is if it's a curve, have one nice smooth curve. If it's just a straight line, again, use the ruler to draw a nice straight line. But I felt like this student did a really good job on those 5 things, and so I want to make sure that this was kind of the one that I used to demonstrate. Now, the one thing that I would mention that could have been helpful for the student is they did 1, 2, 3, 4 squares for 0.25, and they were very consistent about that, which is good, but it would have been easier if they had just gone 0.05, 0.10, 0.15, 0.20, 0.20, 0.25. So if they would have just made each one of those lines 0.05, it would have shifted everything over a little bit, which would have used a little bit more space, and it would have made it a little bit easier to estimate. I mean, this line in the middle for this student is going to be 0.125, which you could do that, but it is going to make it a little bit harder to estimate exactly where those points should be. So I would suggest make sure you're using the grid lines and make sure that you know what each one of those means, and it's going to simplify your life for you a little bit later when you start to put the points on the graph. All right, now with this, we talked a little bit in class about the curve and about the slope. Okay, the one thing that I want you to recognize off the bat is that we notice that the line is changing, right? Here at the beginning, the line is pretty not steep, okay? And as we go on, the line gets more and more and more steep. Now, that's the slope, right? And hopefully in math class, Algebra 1, Algebra 2, Geometry, learned about slope. That's going to be really, really important here. Now, what does the slope actually mean? Well, what a lot of you recognized is that at the beginning, it didn't fall very far, right? So after 0.25 seconds, it only fell less than half a meter. But if you went another 0.25 later, all the way up to 0.5, it's all the way up here past a meter, right? So it traveled further in the second quarter of a second than it did in the first quarter of the second. First quarter of a second, it didn't even make it half a meter. But by the second quarter of a second, it had gone more than a meter, more than twice as far, right? And if we go another quarter of a second, that's beyond what we did even, right? And so we have this idea of the longer it goes, the further it's traveling in that same amount of time. Well, when we say that we travel a larger distance in the same amount of time, what that means is we have a higher speed. Remember, distance over time is speed. And so if we're traveling a further distance, that's my y-axis there, if I'm going a further distance in the same amount of time, that means I'm going to have a higher speed. So we put those two things together, we recognize that the slope was getting steeper and steeper, so a higher and higher and higher slope connected to a higher and higher and higher speed. And what you'll notice, if you look at the units, the y-axis is in meters, and the x-axis is in seconds, so the slope, remember, slope is the change in y over the change in x, or y2 minus y1 over x2 minus x1. Well, y is in meters, and x is in seconds. So your slope is meters per second. It's speed. And so anytime you have a distance time graph, the slope is speed. All right, now we're going to look at a couple other types of graphs going forward, but that's a big one right now. Now, I'm actually going to do some math here. I'm going to talk through the first one, but then I'm going to do it really quickly just so you can see what we're looking at. So what I'm going to do is I'm actually going to try to estimate the speed here at the beginning. So I'm going to look at my graph, and I'm going to do my best to kind of try to draw a slope that matches the slope right here at the beginning. All right? And then I'm going to try to continue to do that as I go down the graph. So I'm going to try to choose another place where I have a slope, like right here, right? And I'm going to choose another place. Notice that the graph is, my line is matching kind of the slope of the curve right there, right? And I'm going to do this again. I'm going to do it again, like right here. Okay, so right there it matches, and my new line kind of matches the slope of the curve right there at that point. Okay, now if I do that several times, then I should have several different points at which I can have slopes. Now remember, the slope is the speed. Okay, so what I'm going to do now is I'm going to go through and I'm going to find the slope of each of these lines, and then I'm going to put it on a new graph so that we can look at what is the slope or the speed at this point, what is the slope or the speed at this point, what is the slope or the speed at this point. All right, so hang with me. We're going to do that really quick. So remember, what I've done here is I've taken several points off of that original graph, and I found the slope at each of those points. And what I did is I plotted the value of the slope. So at this time, the slope was 1. At this time, the slope was about 2.5, right? At this time, the slope was about 3.5, right? And so I just found the slope at various points, and so this shows what we saw there, right? As time progressed, the slope got steeper and steeper and steeper. And so the slope, or the speed, is what's being represented here in this graph. And you'll notice that when I take those points, the graph of the speed versus time actually looks somewhat linear. Take our ruler here, and we're going to draw on a straight line to represent the speed versus time. This one's a linear graph. Your distance versus time was quadratic. Your speed versus time there is linear. Okay? Now, the slope of this means something as well. Just like the slope, remember this was our first graph here, and we found out that the slope of our distance in time graph was representing the speed. This is now the slope of our speed versus time graph. Now, remember again, slope is equal to the change in y over the change in x. And y in this case is meters per second. And then I'm going to divide that by the time, which is seconds. Now, those don't cancel out, right? If I do meters per second divided by seconds, that's the same thing as meters per second times the reciprocal, 1 over seconds. You'll notice that both of the seconds are on the bottom there, so they don't cancel out. I end up getting meters over seconds squared. Now, that's the unit of something that we call acceleration. Now, we'll talk more about acceleration soon. You remember it was in the previous video and we didn't quite get to it, so we'll talk about acceleration soon. But what I want you to recognize is that the slope of the speed versus time graph is acceleration.
So what I'd like to do now is go through a couple of examples and see if we can figure out some information based off of a graph that we've been given. All right, so we're going to go ahead and start with these 6 questions for this distance versus time graph. All right, now what I encourage you to do is when I ask the question, pause the video right away so that you can try to figure it out, and then restart the video and I'll talk you through the answer. Okay, that's actually much better for your learning than you just passively sitting there and watching. Okay, so go ahead and do that, and here we go. First question is, where is the object at time equals 1 second? All right, so at 1 second, we would go over here to the graph. Here's our time, 1, 2, 3, 4, 5, 6, so we go to 1 second, and it's better to use a ruler if we can. So we'll kind of use a ruler to make sure that we're figuring out exactly where we are at 1 second, and you'll notice right there that at 1 second, we are right at 2 meters. So we're at 2 meters from the start. Okay? Now, the second question is, what is the object's speed at t equals 1 second? Okay? Now remember, speed or velocity we can get from the distance versus time graph, and it's the slope. And so what we'll need to do is we'll need to pick a couple of points on that line to get the slope of the line. This is a little bit easier than the one that I introduced you. The one I introduced you was a curve. This one's a straight line, so you know how to get a slope from that. Go ahead and give it a try. I'm going to pick the origin. I like the origin because that's 0, 0. That makes the math easy. And then I'm going to choose this point up here, which is 2, 4. And so in order to calculate the slope, I'm going to do y2 minus y1 over x2 minus x1 And so this one was 2 comma 4. So I'm going to go 4 minus 0. And then x value of 2 minus 0. And I get a slope of 2. The units are meters on the top, seconds on the bottom. So my speed is 2 meters per second. Now it's speed, so 2 meters per second is the correct answer. I don't have to do anything else with that. All right. Next question is, what is the object's velocity at t equals 3 seconds? Okay. So velocity, remember velocity and speed are very similar. The only difference is that velocity is a vector, which means we need both direction and magnitude. Magnitude is the value. So I'm going to go over to 3 seconds, 1, 2, 3. And then right there I can see on the graph, there's my 3 seconds. And you'll notice that the graph is flat. You could calculate the slope there if you wanted. You would find that because it's flat, your slope is 0. So what does that mean? It means that your speed, your velocity is 0. Now because it's 0, it doesn't have a direction, right? So in this case, we'll just say 0 meters per second because it's at rest. It's staying there at 4 meters. It's staying at that position for a certain amount of time. And at 3, it's just resting. All right. Question number 4. Where is the object at t equals 3 seconds? Okay. Same thing. We take our ruler. We kind of did this already when we were looking for the velocity. So we just right there. And we notice that that's right here at 4 meters. So it's 4 meters. All right, so we're getting some distances, we're getting some speeds, some velocities. Let's do 2 more questions and wrap this one up. So question number 5. What is the object's displacement at t equals 6 seconds? Now, do you remember the difference between displacement and distance? Number 1, displacement is a vector, so we need both a value and a direction. And number 2, remember distance covers everything. So right there, we've got at 6 seconds, it is right here, -1, -2, about -2.5. So it started at 0, and now it's at -2.5. Remember displacement, all that matters is your starting point and your ending point. And so that means from 0 to -2.5, that means my displacement is 2.5 in the negative direction, which is to the left. All right, so that's how we would look at displacement. Okay, last question. What is the object's velocity at t equals 6 seconds? Now remember, velocity and speed are both very similar. If it's instantaneous, and anytime it just says, what is the object's speed at this time? It's instantaneous. At this point in time, how fast is it going? What is the object's velocity at 6 seconds? At this point in time, how fast is it going? Okay, so remember, velocity and speed, instantaneous, are both very, very similar. The difference is that velocity also needs direction. So we're going to need to make sure that we include that later. All right? So in order to do this, we're going to, again, calculate the slope. You can do this however you want. I'm going to go ahead and use this point right here because that looks like it's about 4, 4. And then this one right here, already I said was about 6, -2.5. All right? With those 2 points, I should be able to find the slope there. And so we'll do y2 minus y1 over x2 minus x1. So we'll use this as my second point. Remember, it doesn't really matter. So y2 minus y1 over x2 minus x1. And so I end up getting 4 minus -2.5. That would be 6.5 over 4 minus 6, which is -2. When I work that out, I get -3.25 meters per second. So what is the object's velocity? Well, it's -3.25 meters per second. But instead of the negative, because it's negative, negative means that it's moving back over to the negative side, which is the left side. So I can tell that it's 3.25 meters per second to the left. And that's our answer. We've looked at a distance versus time graph, so now let's look at a velocity versus time graph. A little bit different. We've got velocity over here on the y-axis, time still here on the x-axis. Again, let's answer a couple of questions. Question number one, what is the speed at time equals 1 second? All right, give it a try. So when I do this, I'm going to look at time equals 1. I'm just going to go up right there. Now, it's very tempting because in the last one, when it was distance versus time, the speed was the slope. But remember that speed and velocity are almost the same thing. Right here, this is velocity on the y-axis. So at time 1, I'm just going to go right over here. That looks like it's about 0.5. And so my speed is 0.5. Right? That's what the graph is telling me. It's telling me the velocities. I don't have to do any extra math, any extra stuff there. The answer is 0.5 meters per second. That's it. That's it. When is the object at rest? Again, it's tempting because of the last graph to say, oh, it's at rest right here. No, no, no. What is its velocity there? Well, the velocity there is 1. That's not at rest. If you're moving along at 1 meter a second, that is not at rest. Okay? So what we're looking for, rest, is when, Sophia, it's fine. At rest is 0 meters per second, right? That's rest. So that's what we're looking for. So where are we at 0 meters per second? Well, that's this right here, right here. So you could say right here, at t equals 0. At t equals 0, we're at rest. Or you could double check. There's another one right there. So at t equals 5, I'm also at rest. So there's actually 2 different points where I'm moving at 0 meters per second, where I'm technically at rest for that instant. Okay? Now I don't stay at rest. I don't get to rest and stay there. But it's kind of like in this positive, I had positive velocity before. Positive velocity just means that you're moving in the positive direction. So let's say that right is positive, left is negative. So right here, I'm moving in a positive direction. At this point at 5 seconds, I stop. And then here, I now have a negative velocity, which means now I'm moving in the negative direction. So what's happening here is I'm moving positive, stopping, and going back in the other direction. So I'm turning around. I'm changing direction. All right? That's a little bit different from what we get from that distance versus time graph. We're going to have some time to practice this and think about it and look at it, but that's what's going on here. All right? Next question. What is the object's acceleration at t equals 1 second? So that's right here. Now remember, acceleration, we learned in the last video, is the slope of the velocity versus time graph. So I am going to pick out a couple of points. I got 0, 0 here. And I'm going to use this point. I like that point right there. So 2, 1 right there. And so we'll go ahead and find our slope there. So we'll do y2. So we'll do y2, which is 1, minus y1 over x2 minus x1. And I'm going to get 1 over 2. Now remember the units, it's meters per second over seconds. So that's going to be meters per second squared. So 1/2, or if you want to keep it in decimals, we could go 0.5 meters per second squared. Now it's tempting to look at these and say, oh, look, the speed and acceleration are the same. Well, they just happened to be the same. All right? Please don't think that just because these two are the same that they will always be the same. That's not the case. Okay? It's just that's how the graph ended up working this time. Okay? Next up, question number 4. How far did the object travel in the first 5 seconds? Now, we haven't talked about this one yet. This is a little bit different. Okay? The way that we get how far is distance, right? So the way that we get how far is we find the area. We find the area under the graph. So between the graph here and 0. Now, this is kind of a weird shape. You might know how to get the area of a trapezoid. If you do, great. Go ahead and do that. If you don't know how to get the area of a trapezoid, then break it up into pieces that you can work with. right? I can do a triangle here, okay? If I do a triangle there, I've got 1/2 times the base, which has a length of 2 there, times the height, which has a height of 1. Okay, so that would be this triangle right here. Now I'm going to find the area of this rectangle right here. Okay, and a rectangle is base, so it goes 1, 2, so it has a length of 2 there, times height, which the height goes from 0 to 1, so 1. All right, and then I got another triangle right here at the end. So that one is going to be 1/2 the base, which has a length of 1, and then the height, which is still 1. And so I can add all those together, and so I'm going to have 1/2 times 2, which is 1, times 1, which will be 1, plus 2 times 1, which is 2, plus 1/2 times 1 times 1, which is 1/2, and so we end up getting 3.5. Now, this is distance, so this is meters. And for those that are wondering, how does that work? How do the units work? Well, remember what we're doing here is we're taking the length, which is in seconds, and then we're going to multiply it by the height, which is the velocity in meters per second. And if you take seconds times meters per second, then that seconds is over 1, and the seconds ends up canceling out, giving us units of meters. So it ends up working. So this is kind of an interesting, neat thing. Not only can we go from distance to velocity by getting the slope of the distance graph, you can go from velocity back to distance by using the area. So hope that's helpful, and you'll be ready for class next time.